Great. So our next speaker is Professor Mor Vered from Monash University, Australia. So she's a lecturer at Monash University in the Faculty of IT. Her research interests are in the field of human-centered explainable AI and in the interaction between humans and intelligent agents. Today she's going to talk to us about human-centered explainable AI as well. Over to you, Mor. Looking forward.
Thank you. Thank you for having me. This is great. First of all, I'm a doctor, not a professor yet. Thanks for the promotion, though. My name is Mor Vered, and I'm a researcher from the Department of Data Science and AI at Monash University. My research interests include explainable AI, they include intention recognition, and I guess one of my biggest research agendas is interdisciplinary research. So today I'll be speaking about one such type of research, which is human-centered explainable AI. And this combines explainable AI with insights from psychology and the social and cognitive sciences. So it's going to be probably a bit different than the talk you just had, but it's okay. So why is everyone talking about explainable AI? And I guess the better question to ask is why now? So explainable AI has been around since the 70s, but recently it's seen a significant resurgence. And the answer to that is very, very simple. It's because of the increase in deep learning algorithms. So as you know, we have machine learning algorithms, and they provide systems with the ability to automatically learn and improve from experience without being explicitly programmed. And then deep learning is a subset of machine learning where we have artificial neural networks learning from large amounts of data. Now, this is similar to how people can actually learn from experience. So deep learning algorithm performs the task repeatedly and each time tweaks a little to improve the outcome. Now, the recent rise in the success and popularity of deep learning models is largely due to the staggering amount of data that is now available to actually learn from. So with deep learning and machine learning models being used more and more everywhere in medicine, in the criminal justice system, in financial markets, in our phones and social networks, then we really need to understand these models, and it becomes much, much more critical. So I want to just quickly give a few examples as motivation to why interpretability and explainability of these algorithms is so critical. Now, since deep learning is a data-driven model, we have to consider that the data has to come from somewhere, and usually it comes from people. And people, unfortunately, are inherently biased. So I want to give you an example, the case of Eric Loomis of La Crosse, Wisconsin. So this was back in 2013, I think. So Loomis was accused of driving a car that had been used in a shooting. And the COMPAS scale, which is Correctional Offender Management Profiling for Alternative Sanctions, it was used to help determine his sentence. So this scale is generated by a machine learning algorithm that provides an estimate of the likelihood of someone committing a crime based on information of their past conduct and other information that it has. Now, this is by a private company called Northwest, and it is not exactly clear how it works because it is their intellectual property. So that means that this scale, although it is openly used in court, the actual algorithm that disclosed it and the properties that were used cannot be disclosed because it is intellectual property. So it's therefore impossible for Eric Loomis to come up with a defense against this score, which the judge actually used to determine his sentence. Now, since then, concerns have been raised about the COMPAS score being correlating the race of the defendants with a higher likelihood of reoffending. And there's, in 2016, there's been researchers that found that Blacks are almost twice as likely as whites to be labeled a higher risk, but not actually reoffend by the system. So there's a lot of controversy around that. Now, one possible reason for this is the data. Now, the data comes from existing cases, which include a majority of Black defendants. So even though the algorithm doesn't consider skin color directly as a feature, this information is embodied through other demographic information, such as address, such as economical status. So again, because the data is biased, because people are inherently biased, this is a problem. Now, another problem with relying on data is that this data is not necessarily, even if it's not biased, it's not fully representative of where it will be deployed. So one immediate example that comes to mind is medical research. So there's an ongoing failure of research tools to include sex differences in study design and analysis. In fact, often guidelines based on the study of one sex are generalized and applied to both. And one such example is research for coronary artery disease, because it is far greater in men than for women, even though women are, as an older age group, suffer more morbidity and mortality. The conclusions from the male-driven research are implemented when treating both men and women. So again, problem with the data. Now, the last data-driven problem that I will just touch upon is that even if the data is not biased and it's not targeted towards specific populations, the environment in which we live in is not stationary. So data that was relevant before may not be relevant anymore. So consider, for example, product recommendations, right? All the big industry players with AI components supply these. We have Netflix, which recommends shows. Amazon recommends further purchases. Facebook recommends new connections, etc., etc. But our preferences are not static. Neither is our environment. They're new product being introduced daily. And people also change their mind. The problem with this is that it perpetuates a certain situation and doesn't let people be exposed to new things. Now, aside from the data possibly being problematic, sometimes the output itself is not enough. So the most common evaluation matrix for deep learning, for machine learning models, is that you require only the predictions along with the ground truth, and then you produce a score. And sometimes this score is not enough. So let's look at a completely hypothetical example. Let's say we have a deep learning network which is trained to predict the risk level of a person developing lung cancer. Now, the system draws information from an existing database containing electronic medical records, so international cancer patients' medical records, demographic information, lifestyle analysis, and domain expert knowledge. Now, the network outputs for a certain person that they're extremely likely to develop lung cancer. That's not enough. Without any form of explanation, people would question this output. And also, even if assuming that they trust the model, they can't act on this, and they can't act to improve their prospects because they don't know exactly what contributed to their high likelihood. So this is actually very similar to the case of Eric Loomis. He couldn't put up a defense because he didn't know why he was branded like that. So this is why we need explainable AI. So as I mentioned before, it's been around since the 70s, but it's now increasing. And it's actually being defined as one way in which an observer can obtain understanding and interpretability of a model. So the purpose of the explanations is for the output of an AI system to be understood by humans so that they could trust it more and accept it more, and in certain cases so that they could actually fix it and find out what is wrong with the output. Now, this is in clear contrast to the concept of the black box of machine learning, where sometimes even the creators of the model, they don't exactly know why it came up with the output that it did. Now, originally, the explainable AI was researched for the designers themselves to be able to understand and improve on their own algorithms. But now it's becoming increasingly important to explain these decisions to the actual end users. And this is where human-centered explainable AI comes in. So when considering what explanations should look like, human-centered explainable AI considers the end users in that process. So it considers that explanations need to be consumed by people. So they need to be tailored to address human understanding and people of various places in life. Now, to be able to do so, current research, again, adopts an interdisciplinary approach. So it involves information from social sciences, from human behavioral studies, and it focuses on finding kind of causal explanations that can be easily understood by everyday people. So some examples. Lessons from psychology tell us that people understand better through contrastive explanations. So explaining why a certain agent is performing a certain action by comparing it to other possibilities. So for example, you should take this route to get to your location because it is shorter than some other route. That gives us some more information. Another example could be providing information about trigger causes and not about enabling causes. So trigger causes reflect the immediate and the obvious cause. For example, in a fire, you drop a lighted match onto a stack of newspapers and that started the fire. So the lighted match is the trigger cause. But the enabling cause, they reflect the preconditions to the event. So that means being a stack of newspaper, or even more primal, the presence of oxygen in the house, because we can't have fire without oxygen. Now, usually the trigger cause gets the attention, but it's not always the best cause to address. So firefighters, when they fight fire, they're actually targeting the enabling cause of oxygen. So they deprive the fire of oxygen by spraying foam, and thereby they fight the fire. So, and also worth considering is that probabilities and likelihoods, they're not usually how people best explain events. That explanations, they're not always fully presented, so you don't give all of the information you have. People don't want to learn the whole story. They just want the shortest explanation that explains the most things. And finally, explanations, they're social. It's a conversation. It's a social event. It's an interaction. You don't just say this because of this, but you answer questions. So this all needs to be taken into consideration when trying to explain to everyday people. So if we get back to a former example, let's look at an explanation which isn't necessarily focused on the end user. And these types of explanations usually focus on the most contributing factor. So the system outputs that the most contributing factor to this output is the person's age and the fact that the person lives in Norway. So this information, as is, doesn't help the person or offer any suggestions as to what that person can do to reduce the likelihood. And without an explanation, this actually could seem rather odd and evoke a sense of distrust in the system. But when I attempt to delve deeper behind the algorithm, we learn that people who live in colder climates, they're more likely to consume alcohol, which is usually consumed along with either firsthand or secondhand smoke, and that is a direct indicator of lung cancer. Now, to obtain this explanation, we needed first to understand that the previous explanation wasn't enough. So this would be an interaction. We also needed to contrast trigger and enabling causes and to know which one to talk about. So now that I've hopefully sold you on the concept of human-centered explainable AI, I'd like to talk a little bit about some of the research we're doing, which aims at developing these human-centered explanations, and we're adding them to the actions of autonomous agents. And by autonomous agents, I mean any kind of intelligent agent that is used as part of an autonomous, usually multi-agent system. And this multi-agent could be with multiple agents or with people. And these explanations aim to help a human supervisor monitor and potentially identify faults, threats, or places to intervene when interacting with these agents. So some examples range from military scenarios where we have human agent teams and assorted of unmanned vehicles. We have search and rescue missions where automated robots are deployed, and we have firefighting operations that also use robots. So we want to use these explanations to increase trust from the human supervisor or team member, and then increase the utilization of the agent. So in the time I have left, I'll talk about two specific research directions that we've been working on, and where the cognitive inspiration is very apparent. Okay, so the first aspect that we investigated was transparency. Now, transparency, sometimes it's being said synonymously as explanations, but it's one way to explain, but it's not exactly the same. Transparency is actually an agent's ability to convey information regarding its internal reasoning process and the possible outcomes of its proposed actions to a human operator. So it can give me information about how it comes to a decision. This is not necessarily the same as explanations. If you think about LIME, an explanation is something that is added on post hoc and doesn't necessarily know how the algorithm works inside. So increasing transparency, it has been shown in research as an effective method for increasing the operator's trust. But it's a fine balance because transparency means more information. So too much transparency, you could be overloading the user, and too little could be not enough. So we came up with a 4-level transparency model and based on Ensley's model of situational awareness. So true to the interdisciplinary form, Ensley's model it's a widely used model of situational awareness, and it models how people come to an understanding of their situation and make time-critical decisions. So the logic is that if we present an agent's reasoning in this manner, it'll be natural for a human observer to achieve an understanding of the agent's reasoning. So these are our 4 levels. The first level is no knowledge. This is level 0. This level provides no explanation, just the output of the intelligent agent. So just the final decision. The second level is the perceived input. So this level presents the basic factual information about the input as perceived by the agent. So there are no inferences yet that the agent is making, but we can know how the agent has came across that input. So this is sufficient for a user, for example, to detect errors arising from misunderstanding or missing input. Now, the third level, input reasoning, is the immediate inferences that the agent is making based on that perceived input. And this is actually a level that directly corresponds to Ensley's level 2. So let's use an example to show what this means. We have an agent, and it's making a decision about whether or not to deploy a specific unmanned vehicle on a mission. Now, this level 3 information would be, for example, not to deploy this vehicle because of ramifications of weather conditions on the potential performance of this vehicle. So this vehicle doesn't do well in stormy weather, and it is stormy outside. So this is some kind of a inference. Don't send this vehicle. Now, this level doesn't address any specific plan or future action or hypothesis about the future, just the immediate inferences from the input and the knowledge that the agent has. And the final level is the plan projection. So this is predictions that the agent makes regarding future events and the uncertainties or certainties of these occurrences. And this level would also contrast plans to each other and explain why a particular plan of action is actually preferable than another plan. So if we continue our previous example about deploying unmanned vehicles, this explanation would include information as to send vehicle A because the estimated travel time is the shortest from all of the possibilities. So this is our 4-level transparency model. And then we've also tested 2 possibilities for how people acquire this information. People can either acquire this information sequentially. So that means that as it is hypothesized that people do, go one at a time through the whole level, through all of the levels, or they could just acquire it by demand and they can skip levels at will and just go into specific information. So we tested our model on a scenario which replicated a highly complex military planning task, and this was in collaboration with the military. And we wanted to make this scenario as realistic as possible. So participants were asked to surveil a set of offshore and onshore assets using a range of unmanned vehicles. And we wanted to make the scenario complex enough that participants would have to rely on the advice of an intelligent planning agent. And that way we'll be able to evaluate their performance and which transparency information was relevant to them. Now, the agent provided people with 2 different plans, and the operator had to select either one or the other as being the best plan, or indicate that neither is actually suitable. Now, in order to make this really, really complex, we included 12 different UAVs with a range of 9 different capabilities. And this comprised both volatile capabilities, which refer to capabilities whose values may change over time. So you needed to kind of keep that in mind and track them when you're thinking about future plans. So this is like fuel and firepower. And then non-volatile capabilities, which are always constant, like does that vehicle have night vision or not. The mission also had to comply with the rules of engagement. For example, if the incident is a terrorist attack, we must send at least 2 unmanned vehicles. At least one of them must have offensive capabilities, and they must be able to communicate. So, and then there were quite a bit. There were 6 different mission objectives, and there were quite a bit of rules of engagement for each one. We only gave participants 4 minutes per task, and that made them rely on the advice of the intelligent agent, much as it would be in a real military scenario. Now, participants for this experiment included undergraduate and graduate students from our university, and I'll just skip particulars. Okay, so I won't go into all of the findings in detail, but our general take-home messages were that participants responded really, really well to having that transparency model, and they reported higher perceived trust in the agent's advice. They performed better overall and in significantly less time. Now, the situation awareness model enabled participants to spend less time on unnecessary information. And so we also gained some insights as to which transparency levels interested people and in which order. And this in turn gives us more information to how to explain and which explanations to provide. I'm just conscious of time. So if this interests you, I'm happy to send you the paper and discuss further. Just shoot me an email. So the second research project that I'd like to discuss is actually an ongoing project. And in this one, we're actually investigating 2 different types of explanations, also inspired by cognitive sciences. So these are global and local explanations. So global explanations focus on how questions. So that is, how did the algorithm or the agent come up with that decision? What is the process that the agent takes? Now, an important goal of explanation is to help the user develop kind of a mental model of the system, how the system works in general. And global explanations, they do that. They reference conceptual categories and mechanisms, and they provide information about the training, about where the algorithm fails in general, and how the algorithm succeeds. So they're general, but while they can help a user to begin to understand individual decisions, when they're faced with a particular instance that the user doesn't understand, then they can't really explain that one. And that's where we would need local explanations. And local explanations answer why questions, why a particular decision was made. And they emphasize specific instances and attributes, and they tie them to specific activities and context. So for an image classification method, a lot of them provide local explanations in the form of saliency maps relative to a specific image. But again, the same aim, to help the user build a robust mental model of the system. So one way is through a general understanding, the other way through particular instances. So from general to specific. So again, we conducted an experiment to evaluate different forms of these explanations and assess their effects on human users. We instantiated and evaluated both global and local explanations on a task called colored trails. So we came up with our own unique colored trails. If you're not familiar with it, It's relatively well-known research platform for analyzing human decision-making strategies. It's quite complicated. I'll just try to convey the main concept, but it's not crucial to understand. So it's played on a square board with lots of colors. We have 2 or more players, and players, they're provided with chips with the same colors as the board, and they can give those chips in order to advance towards a goal tile. Now, we developed a new version of the game, which we called One Shot Best Move Colored Trails. And in our game, players needed to reach the goal just at 1 tile. And to do so, they had to create a path on the board, and they had to talk to each other and try to exchange chips between themselves. So again, we recruited participants via an online participation system and divided them into 5 cohorts. One cohort, they just had to play the game. They didn't have any access to any advice, so therefore no explanation was needed. In the second cohort, they had an intelligent agent giving them advice. You should do this, but no explanation. The third cohort, they had an intelligent agent with local explanation. The fourth cohort, global explanation, and then both. Now we used So we used actually a form of visual local explanation, and what it looked like was it was a highlight of the search space in the grid where the IA searched for possible paths, and it had a written local explanation statement. And this was local in the sense that it related to only one instance, one game, and it would change for every game. We had a global explanation, which they would see before the beginning of the experiment, which explained how the intelligent agent worked and what kind of approaches did it take, where it could fail, and where it could succeed. So this enabled us to measure the performance of players with and without explanations, and with different types of explanations. And we also asked participants about their perceived trust and about the IA usability. So this is ongoing work. We're currently running a follow-up experiment on a different domain, but the results have been pretty promising so far. So initially and crucially, we were able to bias the participants. So they did choose the wrong decision when the intelligent agent gave them the wrong advice. And of course, this was crucial so we could measure whether these explanations could actually negate this effect. We were then able to negate this bias using different types of explanations, and we found that different types of explanations were more effective for different types of mistakes that the agent has made. So global explanations were more effective when the solution was a longer path, which was more complex, but local explanations were more effective when the agent failed to consider implicit alternatives, such as doing nothing or that the other agent might do nothing. Overall, the local explanations were the most useful for this particular task. However, when we're now looking at another domain, we see that different types of mistakes, actually, the global explanations are more important. So this, again, is very, very valuable when you're fastening your domain and you're coming up with these explanations to think about exactly how to get to your end user. Now, in future, what we also hope to evaluate is the effects of training and which types of explanations would be better under the assumption that a certain amount of training had actually taken place and certain expertise achieved. So I guess that's it for today. I mainly wanted to touch upon the general kind of high-level idea behind human-centered explainable AI. I wanted to present some of our more multidisciplinary research on that topic, and I'm happy to answer questions.
Thanks, Mor, for the great talk. So we have some questions from the panelists. Mayuk, do you want to ask your question?
Yes, sure. It was a very nice talk. It was really interesting. I just wanted to highlight on the fact and kind of understand the scenario where I was thinking the whys can always be related to the hows in case of local and global explanations, right? For example, in case of algorithmic bias, explaining how a deep model was trained or quantized may explain why an agent can predict things very fast, but may end up making mistakes in many cases, right? So such explanations is like the why and the how are interrelated in some sense. So how
Well,
do we
yes,
go about understanding that?
I completely agree. They are related, and it's the same way that local and global explanations are related. And they, I guess I didn't convey that very well, but they do have the joint goal of, and this could be achieved either way, right? Of you could either learn from very specific instances and answering a why question, or you can learn from answering a how question. And I guess what we were trying to show is that specifically with regards to experiments with humans that we've done, certain kinds of answering these questions, even though that they are so very linked and similar, they have significantly different effects on performance. So when you're explaining in one way or another to a human user, it becomes significant. I hope that answered your question.
Yes, thanks a lot.
So I have a general question. So we are talking about this why and how, right? So should we also talk about the who question in some sense, because the way you give
I'm sorry, I can't hear you.
Sorry, can you hear me now?
Yes, yes, no.
Yeah, so I was trying to ask, is the who question also relevant, right? So as like the why and the how, because it might, so your explanation might convince me, but might not convince an expert in the field probably, right? So should explanation itself be seen as like a two-way communication as opposed to you give an explanation and you're done with it? So what are your thoughts?
Definitely, definitely. So if you look at the social sciences, explanations are an interaction. So and explanations are meant to be part of a conversation, and that's how humans kind of perceive it. And by actually having that interaction, you can develop a sort of a theory of mind of what the other person is knowing, of what that other person is thinking, and then you can tailor your explanations to that person. And people are really adept at doing this intuitively, but it is rarely modeled in agents, if at all. So that is kind of what we're advocating, because up until now, and there's quite few works that are actually actively doing this, explanations are simply, these are the features that influenced it, and kind of, this is kind of the output that's going to go through, at least for machine learning and deep learning models, and less about the other side.
Right, right. So you're saying not much work has happened in that that way of looking at things, at least from a ML point of view?
Exactly. No, it's not very common, but it's becoming more and more increasing. I think since Tim Miller's seminal work, he's got a journal, very famous journal paper about learning from the cognitive sciences. Since then, there's been a trend that is increasing, but up until then, very few people are actually doing it.
Sure, thanks. Professor Kethi?
Yeah, I was wondering whether the question of which question to take up for explanation, for the explanation, itself is an interesting problem. For example, in some cases, you might need who and why. In other cases, you might need what if, and things like that. So, is that a problem that you think is interesting, and how do you go about following up on that?
So that is actually one of the problems that we're actually looking at. What I didn't have a chance to go into too much in the talk is that we have actually defined different kinds of mistakes that could be made by an agent, for example, false positives or noise or things like that. And then we looked at several domains, and we looked if we could see a consistency in which explanations, so local, global, these kinds of explanations are actually better fit to each of these mistakes. And we actually found quite consistent results, even though we went in completely different domains. So there definitely is something that people kind of want to hear when they see a certain kind, or need to hear when they encounter a certain kind of bias or a certain kind of result, error on the side of an automation that helps them clarify things.
Okay, great. Are there other questions from the panelists? Okay, so maybe I'll ask one or two questions from the chat box. Okay.
Arun, you can be a bit more louder. I think it's not audible.
Oh, okay. Okay, is this better?
Yeah, it's better now. Yeah.
Okay, I think one of the questions was about the computational challenges with respect to global versus local explanations. Are there any concerns there?
So I think the biggest difference is the online versus offline. So if you're doing a global explanation, in a way it can be computed offline and presented because you do give examples, but you give general examples. You kind of tell how it works in general. When you're doing online, when you're doing local explanations, it is an online process because you're giving explanations about a specific example. So I think the kind of computational load would be a bit, is more intensive in that way. Of course, global explanations need to also be updated, but still local explanations seem to be more computationally expensive.
Okay, great. Any other questions? Okay, I guess there are a few more questions on the chat box. If you have some time, maybe you can take a look at them and answer the relevant ones. Okay, so
Can I ask a question? A quick question?
Please go ahead.
Okay. Certain cases, the domain might be such that some questions are going to have a static answer. No changes happen with any with respect to dynamics. In other cases, the dynamics might make a difference in terms of whether it changes or not, how much it changes, and so forth. So, how relevant is this question of dynamics, and also is it going to increase the computational complexity of the problem so much that you don't want to touch it? I would expect that it's going to change the complexity of the problem quite a bit.
Well, I think that's an interesting question that I haven't actually addressed, so I can just answer off the top of my head.
Okay.
But I think it will increase the complexity simply because as explanations need to be contrastive, you would then need to generate, same as Lime does, you need to generate permutations within different dynamic constraints in order to be able to provide an explanation, even if it's not asked for directly, but in order to provide that contrastive explanation.
Okay.
Okay, thank you very much.
Okay, thank you, Mor, for the great talk, and thank you again. Yeah.